Hello. Good evening, Sandeep.
Yes, ma'am. Good evening, ma'am.
Yeah. So, so we are here to discuss the fourth assignment of the NPTEL course Symmetry and Group Theory taken by Professor Anindya Datta from IIT Bombay. I'm Shruti, a PMR PhD scholar from the same department. So, shall we start? Did you solve the assignment?
Yes, ma'am. I tried, but there were few mistakes from my side. So,
Yeah. Okay. So the first question is switching of bases is achieved by Fourier transformation, unitary transformation, Laplace transformation, or similarity transformation. So this I hope you have got this correct.
no, ma'am. I did actually unitary transform, but the answer is similarity transform.
We yeah,
We
answer
can,
should be similarity transform. No,
but we can use unitary transform also for
what is unitary transformation? First, tell me that.
uh, that is x inverse ax is giving b, and there x inverse is also unitary, and a is also unitary, and b is also unitary.
So isn't
So
this a special case of similarity transformation? Whatever you told.
yes, if it is a special case, then it should also be correct, no? Because it is
No,
more refined.
but the basic, like the actual method behind the unitary transformation is similarity transformation. We are finding conjugate anyway in the unitary as well. Fourier and Laplace transformations are different, but unitary transformation is a similarity transformation. So this is a more general case. So that's why the correct answer is this one.
Ma'am, what is the difference between the similarity transform and unitary transform?
So unitary. Okay, this is a similarity transformation. Okay, now when this is a unitary matrix and this is a unitary matrix, okay, then this transformation will be called unitary transformation. Okay,
Yes, ma'am.
so isn't this a special kind of transformation? Basically it is a similarity transformation only. We are finding conjugate of A with respect to the matrix X.
So, in the case of similarity transform, that X can be any other matrix, na? Any
Yes,
matrix.
any
Eh,
other matrix, any kind of matrix.
Is there any restriction on X that X should be certain kind of matrix only? Then only it will do symmetry transform.
No. There is no restriction. You can use any other element of the group. But for switching for bases, there are certain restrictions actually. But for like in group, you can use any other element of group to find the conjugate of this element A. Like in last class, we did, right? You
Yes, ma'am.
remember the
Yes,
last
ma'am.
question?
Ma'am, actually, I was going through the bishop, and in the bishop they had said that for orthogonal transformation, for orthogonal basis sets, that this unitary transformation is usually used. So, if any one orthogonal set to another orthogonal set, if one unitary transformation can do, then what is the use of unitary transform? Because anyway, we are using all the orthogonal basis set, no? Orthogonal basis set.
But
So
unitary transformation is a similarity transformation. The process is a similarity. The process is finding a conjugate. It is just that we are using a unitary matrix.
okay, ma'am, but that answer is also okay, na? If somebody is writing the unitary transformation, because switching of basis is also takes place via unitary transform, and it is a special case of the similarity transform. So
Yes,
it is it is always
not
true
always
that
the basis will be
similarity transform
orthogonal.
will convert from one basis to another basis. It is always true.
Not always the A will be orthogonal, na?
Yes, yes, ma'am.
So similarity transformation is the correct, like the best answer here.
Okay, ma'am. Okay.
Okay. So next is, if Q inverse AQ equals to B, then trace of A is equals to trace of B minus of trace of B, greater than trace of B or less than trace of B. This was done in class, right?
Yes, ma'am. Equal to trace of B. Equal to trace of B.
Yes. So it is equal to trace of B. But let's see for others. I'll do it once more. So Q inverse AQ. Also the second question, Q inverse AQ is equals to B, then determinant of A is equals to, this also is,
True, ma'am. True, ma'am.
this also is
Remember.
same as determinant of B. So
Yes, ma'am.
let's solve both of them together. Now A and B are conjugates, right? So simply we can see by similarity transformation we find conjugates of one element to the other. So A and B are conjugates, and we know that conjugates belong to same class, and also this consequence, there is a consequence of elements belonging to the same class, that is they have same character or trace. Character is also known as trace. Okay, so let's write trace of B is equals to diagonal sum of diagonal elements, which is BII summation I, and since B is equals to Q inverse AQ, we can write it sum of I, sum of J, this is a multiplication, so this should be K, this should be, the first index should be J. Okay, now we can separate A out, so Q inverse Q will give us identity, summation J and K. So Ji will be Q and Q inverse will be Ik. Now this can be multiplied because this index and this index is same. So this will be summation J, summation K, Q times Q inverse Jk after multiplication. So we had summation j summation k. Now this is E of jk, akj and ej and k. Yeah. So now even if you multiply or don't multiply, it will be now when these two are same. So there are two options here. When j equals to k, this is the definition of identity matrix. That is, it is a Kronecker delta jk. So when these two are not equal, the whole thing goes to 0. Okay, so there is no point of taking that. Anyway, we are calculating trace, which is the indexes should be same. So we are taking j and k to be same. Let me write summation k delta jk. And from this one summation goes, we are left with only one summation, either k or j, you can write anything. Summation a j, ajj. So this is equals to trace of a. So we started with trace of b. Now this comes to be equal to trace a. So that's what this. So after similarity transformation of the conjugates, the trace remains same. So that's why the characters or the characters of elements or operations in the same class have same traces. Now the next one was determinant. Q inverse AQ is equals to B, then determinant. Okay. Now we can write like determinant, how the determinants are got multiplied. If xy is the matrix, then the determinant, this will be determinant of xy will be equal to determinant of x determinant of y. This is a property of determinants. Okay, so you take this side, determinant of b is equals to, you take this as one quantity and take this as the other, so it will be determinant of q inverse determinant of aq. Now we can uh, simplify this as well. Determinant q inverse determinant a determinant of q. Now if I can write like this, I can write the reverse also, and since the determinants are numbers, I can write it like q inverse. Now this is not anymore matrix multiplication, so I can write it like this. and I can write it as Q inverse Q determinant A. Now Q inverse Q is equals to identity for any identity matrix. This determinant is equals to 1 for the unit matrix. So this comes out to be determinant of A. Therefore, even after performing similarity transformation, the determinants remain unchanged. The trace or character remains unchanged, and also there is one more property, that eigenvalue remains unchanged. Okay, so these two questions were related. Now next is, for a Hermitian matrix, eigenvalues are always, Sandeep, you made this one correct?
Yes, this was discussed in the previous class, so it is real. Hermitian
Yes.
matrix eigenvalues are real.
Yes. Can you prove this one? I this is also done in quantum courses. So eigenvalues are real. Why? Because the diagonal elements are real. Okay. So let's try to prove this one as well. Now Hermitian matrix, what is Hermitian matrix? Which is equal to its adjoint,
Yes.
self-adjoint. A is equals to A dagger. And how we find eigenvalues? A xi is equals to lambda I xi. My lambda looks like x. Okay, so we can take adjoint. Now similar to matrix multiplication, adjoint of product of matrices also follow the inverse order, like this. So AXI dagger will be XI dagger, XI dagger, A dagger, and this is a number, so this will be star XI dagger. Okay, now A dagger is equals to A, so XI dagger A is equals to XI dagger. Okay, now we have to remove this x, so we can do right multiplication here. Right multiplication by xi, so it will be xi dagger A xi is equals to Okay, now this part, so from this one, from this equation, we can write that this AXI is equals to lambda I xi. Okay, is equals to lambda I star xi dagger xi. Now since this is a number, we can take this out. Lambda I xi dagger xi is equals to lambda I star xi dagger xi. So, and we can take this on one side. Xi dagger xi equals to 0. Okay, since xi star, this part, this won't be equal to 0. Why? Because these are eigenvectors and they are orthonormal. So it will be like x1 star x1 plus x2 star x2 and so on. So this won't go to 0, which means that lambda I minus lambda I star goes to 0, or lambda I is equals to its complex conjugate, which means that lambda I is real. Because for real numbers only, x is equals to x star, means the number is itself equals to its complex conjugate. So we say that for Hermitian matrix, eigenvalues are real.
Ma'am, I have one doubt in that. Uh,
Hmm?
in quantum mechanics in general, uh, actually this is true for the uh, non-degenerate eigenstates, na? Or is it true for even for degenerate eigenstate? This statement,
Okay.
uh, all the eigenvalue must be real. This is true for all the eigenstates or for all the
No, no, it is true for all states.
all states, na?
Because even for, suppose we are taking uh,
Ma'am, because
Hamiltonian. So
yes, ma'am.
even if Hamiltonian is giving degenerate states, those degenerate states have real energies.
Yes, ma'am. But the energy will be same. So when
Yes.
we are subtracting the energy, then energies are same. So those values will be zero, no? But
For
the but even in that case, the
no, this subscripts will change now. Fir I, this will be ij. If these two states are different, lambda I minus lambda star j, it will be j. If we are taking two different states.
ma'am, it will be J, it will be J only. But as the states are degenerate, so
Yes,
energy
so
will be same. Energy
energy will
will
be same. Yes.
yes, energy will be same, and also those two terms will go together zero because
Yes, yes.
xi and xj both will go zero
So
because
in that case, it will be like this. Like this is for one, and this is for G. We will use different subscript
yes, ma'am.
because those are two different eigen states, eigen values. So They are same, that is true. That's why they are degenerate, but they are real.
Yes, ma'am. So in that case, xi and xi star is also zero, no? Xi and xi star, those eigenvectors, because eigenvectors will be orthonormal. So
Yes.
even for degenerate states, the eigenvectors will be orthonormal.
Yes, yes.
So both eigenvalues will be equal, as well as eigenstates
The
will be orthonormal.
eigenvectors will be same.
Yes, ma'am. Eigenvectors will be different now, ma'am.
If eigenvalues are same, then they will have same eigenvectors.
No, ma'am, it will be different now. Like when we are doing particle in a box now. So if we are n1 n2, we are changing now. Uh, like uh, uh, like root under 2 by L into root under 2 by L. Then sine kx by L. Then sine ky by we are taking now. We are taking n1 and n2, two quantum numbers we are taking now. Two quantum numbers we are interchanging, like first excited state is 1 2, then 2 1, both are degenerate. 1 2 and 2 1 both are degenerate. Like n1 and n2 value, we are interchanging n1 and n2
Yes,
value.
yes. But eigenvectors I'm talking those are eigenstates.
Yes, ma'am. Eigen states will be different, but the eigen values will be same.
Huh.
Yes, ma'am.
Now the fourth one is choose the correct properties of transformation matrices. Always produce unitary representation. They are nonlinear and they are linear, or they changes the scalar product of two functions. You did this one, Sandeep?
Yes, ma'am. It is linear. It was discussed in the class.
Yes, it was discussed in the class, but anyway, it is very confusing. So the answer is linear. Now, as I told in the beginning, that transformation matrices produce unitary representations only if the orthonormal basis functions are used. Okay, so this is not general. It does not always produce. If you use any other basis function, the representation may not be unitary. Now, it is a linear. This one is wrong. It is linear. What do you mean by linearity?
Actually, when we are multiplying the function, like fx is a function, fx. So if we are replacing x by kx, then the entire function should get multiplied by k. F of kx is equal to k into fx.
Is this you're telling?
Yes, ma'am. Yes.
Yes. So if you multiply the whole thing, the function by a scalar, a number, then the number can be taken out and it can be multiplied individually. And also, if there are three functions, and then we can write one in terms of the other two. So now here it is asked like transformation matrices. So if transformation matrices or operators, so if you are writing operator, a transformation operator for the symmetry operation R, and this is the function applies on x1 dash, x2 dash, and x3 dash, then this will, since this is a definition that it leaves the coordinate as x1, x2, x3, means this is the initial coordinate position vector g, and after doing the operation O for the symmetry operation R, the coordinates become x dash, x1 dash, x2 dash, and x3 dash. Okay. Now suppose this g is a combination of a scalar and a function a times any other function f. Okay. Now this, the inverse relation from here we can write at a operation operating on function f giving x1 dash, x2 dash, x3 dash. Okay, f and g are functions, a is number. A is a number such that g is equals to af. So whatever operation we do on g, it will give that operation multiplied by a. It's like these two will be same. So this is called linearity. Also the other thing, that if there are three functions, we can write they are linearly h is equals to f plus g. Okay, if this is a linear sum of two functions, then the operation of an operator R for symmetry, of an operator O for symmetry operation R on F, it will give me x1, x2, x3. So this is a reverse way of writing. When we are doing, now this gets changed, x1, x2, x3 gets changed to x1 dash, x2 dash, x3 dash on applying this operation R. Similarly, we can write for the same symmetry operation, we cannot change the symmetry operation. If this is another function, okay, now we can write the sum of these two is equals to And now f and g are sum of f and g equals to h. So we can write it h times x1, x2, x3, and we can use the definition ORH is equals to x1 dash, x2 dash, x3 dash. Okay. And the fourth option is changes a scalar. The transformation matrices changes the scalar product of two functions. So this option is not correct. It is one of the property that it does not change the scalar product. Now scalar product by definition for two functions is given by integration fy star fj d tau. Okay, so if there are two functions, whose scalar products are fi fj, like two functions fi and fj whose scalar product is given by fi dot fj. Now this should be equal to okay. So fi fj is d tau volume element x1, x2, x3. The integration. Okay, now this part can be written as ORFJ, and this part can be written as ORFI star. Okay, so in total it will be ORFI star x1 dash, x2 dash, x3 dash into so it means that as it is written in the book Bishop that all of this math means that transformed function in the transformed coordinates is the same as original functions in original coordinates. So for this question, the answer should be C. This is the correct one. It does not change. This is also wrong. And it is not always unitary. Only when the orthogonal bases are used, then only it will produce unitary representation. So fifth question is, if Q star AQ equals to B and the transformation is unitary transformation, then the matrices must be unitary is R. What is the correct answer for this?
Ma'am, I wrote QAB because a unitary matrix transforms a unitary matrix into a unitary matrix. No? So
Yeah.
I wrote QAB, but the answer they have given is only option A, option B, A only.
Yes. Now, yeah, you are correct. Like, first, when you will look, you will feel that the answer is D, but the correct answer is this only. I'll tell you why. It is it is asking when a transformation will be, what is the must condition for a transformation to call a unitary transformation. So the, as I told you, I think in the first class, key unitary transformation is a similarity transformation. No, this I think is wrong. When we use the x, this may or may not be. So when x, the matrix which we use to perform the similarity transformation is a unitary matrix, then that transformation is called unitary transformation. Okay. So the definition of unitary transformation does not put any constraint on what should be A and B. Okay. Any transformation, if we are using a unitary matrix U, let's not use, let's see P. So this is unitary. These two are not unitary. But still this transformation will be called as unitary transformation. Why? Because the matrix we are using to transform is a unitary matrix. So the must condition for this is that the matrix which is used for the transformation should be unitary matrix. Okay. So the question asks about which is must. The A and B can be anything, unitary or not. It does not matter. until and
Ma'am,
unless Q
ma'am,
is unitary.
but unitary transformation is used for converting one basis to another basis only for orthonormal basis set, na? Only for orthonormal basis set. It means A and B must be related by orthonormal basis set, so they must be unitary also. No?
I am telling you the same thing. It is possible if A and B are orthonormal or unitary. It will work. But this transformation will also work if you take any matrix, unitary matrix, and take A which is not unitary and try to do the transformation. The transformation will work. You will be able to find any matrix here B. Okay. I'm telling you by definition. What is the definition of unitary transformation? It is not only meant for orthonormal basis sets. You can apply unitary transformation. What is unitary transformation? A similarity transformation in which the matrix we are using for the transformation should be unitary. You got my point?
Yes, ma'am. Yes, ma'am.
So it does not put any constraint that A is unitary or not, or A is orthogonal or not. A can be anything. B can be anything. B will be the result of this transformation. So B can also be anything. That special case comes when U is unitary, A is unitary, then B has to be unitary. B has no other option to be anything else. So the answer is A here only. Answer is correct. Okay. So this question is this is the same thing which I told you now, that the symmetry operation O with for the symmetry element R is a function of x dash y dash z dash should be equal to for f of x, y, and z, because the functions itself after transformation and before transformation does not change. So let me write it here. This is the this is actually definition only. The transformation operator O for the symmetry operation R for any position vector Fi is defined as this only. Fi x1, x2, x3, and I can be anything from 1 to n. What is n? N is the n-dimensional space. So x1, x2, x3 is moved to x1 dash, x2 dash, x3 dash after the operation OR. Okay, this is the physical meaning of this equation. ORFI is the new function. When OR was applied on Fi, the coordinates of x1, x2, x3 changed to x1 dash, x2 dash, x3 dash, but the function itself did not change. So ORFI is equal to the old one, these are the original function with original coordinates. Okay, or I can also write it like that: the new function over fi okay. So the new function ORFI assigns the value of the old coordinates x1, x2, x3 to x1, x2, x3 dash. So if we know fi, 6, 7, 8 variables are there. So if we know fi, then if we know x1, the original coordinates x3, and the transformed coordinates, then we can find the matrix representation of the OR. This is the same thing which we did in assignment second, I think, when there was this question of carbonate, right? Or p orbitals were given. There was this coordinate axis y x, and we were asked to find the matrix for some C3, S3 and all. Do you remember? So in that, what we did, matrix was unknown, but we knew the P1, P2 and P3. It got transformed into what orbital? Suppose P3 remained unchanged, P1 and P2 got exchanged. So we knew this one, and we knew F, which is some operation, suppose C3. So based on 1, 2, and 3, 7 things, we could calculate this matrix, right? We did this thing earlier, just now we are writing it in mathematical form. So this is like when we knew F is the operation here, the original coordinates, the p orbitals before transformation and the p orbitals after transformation. If we know these things, we can work out the matrix representation of the transformation operator. Am I clear? So was this question correct for you, Sandeep?
No, ma'am, again it got wrong. This question.
Yeah, because I also have confusion in this question.
Because I think it should be transposed.
Yes, it should be transposed, but I don't know why it is written in the bishop also, it is written same. I have to clarify this one with Sir once, because Sir had told transpose in the
Yes,
classes
ma'am.
as
Yes,
far
ma'am.
as
In
I
the
know.
class, it was told transpose.
Transpose, yes. But bishop has given a proof also that it is same. I don't know why. Maybe we are getting confused with the what does the same means. Same matrix means, so they have given, let me do the proof, but the answer given is this. I think A.53 appendix. So what they have written is there is a position vector which is defined as x1 e1 plus x2 e2 plus x3 e3, and after transformation it becomes p dash. This is the symmetry operation applied on p, so it will be applied on the basis e1 e2, x1 x2 x3 are coefficients, e3. Now these ei's or ek's according to Bishop, the transformed ones, it can be written as REK. Now R has a form DJK J equal to 1 2 3. This is the form for R. So let this be the first equation. So if we put this in the this equation, first one, second one, same thing three times. Just this coefficient will change. And then they have written it, they have taken this, they have changed these indices. So they have written it like this: I equal to 1 2 3. So here we were summing over this EJ. Now we are summing over this I index. and this is transformed x1, and they have written it like kj. So starting from this, it was jk in the first equation, and now we have arrived at this one. This is k times j, which should be the transpose, but I don't know why it is written that both matrices are same. I am also not sure about this. I will have to clarify. So the only one sentence over there is written that uh, the same matrix dr defines xk dash through this equation 2 and sorry xk dash through equation 3 and ek dash through equation 1. So maybe I was thinking that maybe it is because the matrix is same. So once we are using as as a transpose and once we are using it without transpose. For ek we are using it as it is, and for x case we are transposing it. But still the transpose of this matrix will not be same as the original matrix. So the answer should be transpose according to me as well. Okay. Now coming to the eighth question, it is asking the incorrect statement among the following. So we have to find the incorrect ones. Every element in a group is a conjugate of itself. Self conjugate. So every element, so I'm using same, let's a. If I'll do left multiplication by a inverse and right multiplication by a, what will I get? I will get a again, right? So this makes this statement correct. For any element, we can write it as a similarity transformation with itself, with respect to itself. So every element is self-conjugate. And because of this case only, E the identity element forms a class by itself, because if we do E inverse E E, we will get E. Okay, so the first statement is correct. The statement second is AX A inverse X inverse is equals to AX whole inverse, where AX are elements of a group. This also we know by matrix multiplication. This is not true. What happens? The correct answer should be X inverse A inverse. So when we find the inverse of product of matrices, it is in the reverse order, the product of inverse of those matrices. So this is not true. So X inverse A inverse is the inverse of AX. This is what actually means. So you can simply check by putting this dot AX. This should be identity if this part is inverse of this part. If it is not happening, then it is not correct. So here we can see, we can write this as A inverse A X, and this part will be identity. So X inverse I X, and X multiplied by I will be X only. X inverse X, again it is identity. So this statement is, this is true that the inverse of AX is X inverse A inverse and not A inverse X inverse. Okay. So this the incorrect statement is this one. This is incorrect. This is the wrong one. Now C is, if if A is conjugate to B as well as C, then B and C are conjugates of each other. So if A is suppose X inverse A is conjugate to B and C also, some other Y, A Y is equal to C. Okay, so from here we can write A is equals to X B X inverse, and let me put this in this. So C is equals to Y inverse X B X inverse Y, and let me rearrange. Okay, so this also is like a similarity transformation. Inverse, suppose y inverse x c is equal to y inverse x b x inverse y. So if we can take this as any z inverse, this as z, then this is equals to z inverse bz. C is equals to z inverse bz, and this is also a similarity transformation. Okay, now how I have taken this z inverse z, what I have taken, z is equals to x inverse y and z inverse is equals to y inverse z. So when I will multiply z inverse z, I should get identity. Then only these two are inverse of each other. So let's check. Okay, so these two are inverses of each other. So we can write like z inverse b z. Okay, so this statement is also correct that if A is conjugate to B and A is conjugate to C, then A and B are also conjugate to each other. And then A and B, A, B and C will form a class. And the last one is, this is correct. Last one is, a class is a complete set of elements. This is all, this is correct or not? So the definition of, by definition, the class is so we define class as a complete set of symmetry operation which are conjugates to each other. So that statement, D statement is correct by the definition of class itself. Okay, and this one, I think in the last class, last session, the last question was we need to find the different classes of G6 group in the group multiplication table. In that we did, like there were three classes. One was E itself, and the other was A, B, and C, and the third was D and F. So if we do any similarity transformation for each of A, B, and C, we will get the elements A, B, and C, either A or B or C itself. Okay, so we cannot, we perform any similarity transformation, we cannot get D or F. So that's why it is called a complete set. complete set of similarity operations which are conjugate to each other. Is it okay?
Okay, ma'am. Okay.
Yeah. Okay, so this was the last question for today. There were only 8 questions today.
Ma'am, in the bishop, they are taking clockwise rotation as the positive direction. Bishop on Hui book. Hui.
Yes, actually, in the one more book which Sir has suggested, in that book it is written clockwise. So
Yes, but
maybe
in
the
online and also I have seen some Kannada professor, they have written anti-clockwise as the positive. Online it is saying anti-clockwise, but
yes, yes, I know.
some old books are they are writing clockwise.
So it is, I think, for books it is they have written in the starting chapters that from in this book we will take clockwise or anti-clockwise. They have mentioned in the beginning. So I think in every question like this, they should mention that which direction we
Yes,
should take.
yes, ma'am. Because in one question in assignment two, they when they took anti-clockwise,
Anti-clockwise.
yes, anti-clockwise. But in
Yes.
another assignment, they are taking
In the last assignment, they are taking clockwise.
clockwise. So it is not good, now, ma'am. Because
Yes, yes, I know. I got your point. Yes. So I think they corrected the last assignment questions, did they?
no, till now they have not corrected.
No, but I have talked about this. I think they have submitted. I think the correction, the revision.
But one more correction was missing in question number seven or something. Question number three, they had not mentioned because one person had mailed them and they said they will correct for question number six and eight, but question number three was missing. So I have mailed on the forum. But I
Question
couldn't.
number three. What? Let me check. What was this?
Week four question number week three question number three.
Okay. Week three. Question number three. Oh, ha. Question number three. Yes. It is not matching with. So I'm seeing.
Any of the option it is not matching.
Yes. Question number three is that one, na? A minus IB by D, C minus ID by D.
Yes, ma'am. Yes, ma'am.
Yes. Yeah, but I talked about this thing. They said that they will send the revised answers. They will upload it. Maybe it will get corrected.
Okay, ma'am.
Yeah. Okay, so I think that's it from today from my side.
Yes, ma'am. Okay, ma'am. Thanks, ma'am.
Okay. Thank you.